standard conditions for temperature and pressure as standard sets of conditions for experimental measurements to be established to allow comparisons to be made between different sets of data. The most used standards are those of the International Union of Pure and Applied Chemistry and the National Institute of Standards and Technology. Although these are not universally accepted standards, other organizations have established a variety of alternative definitions for the standard reference conditions. In chemistry, IUPAC could have established two standards: standard temperature and pressure as a temperature of 273.15 K and an absolute pressure of exactly 100 kilopascals, standard ambient temperature and pressure as a temperature of 298.15 K and an absolute pressure of exactly 100 kilopascals. The SDP and the SATP should not be confused with the standard state commonly used in thermodynamic evaluations of the Gibbs energy of a reaction. NIST uses a temperature of 20 degrees Celsius and an absolute pressure of 1 atmosphere. This standard is also called normal temperature and pressure. The international standard metric conditions for natural gas and similar fluids are 288.15 K and 101.325 kilopascals. In industry and commerce, standard conditions for temperature and pressure are often necessary to define the standard reference conditions to express the volumes of gases and liquids and related quantities such as the rate of volumetric flow. However, many technical publications simply state standard conditions without specifying them, are often leading to confusion and errors. Good practice is to always incorporate the reference conditions of temperature and pressure. Definitions. Past use. Before 1918, many professionals and scientists using the metric system of units defined the standard reference conditions of temperature and pressure for expressing gas volumes as being 15 degrees Celsius and 101.325 kilopascals. During those same years, the most commonly used standard reference conditions for people using the imperial U.S. customary systems was 60 degrees Fahrenheit and 14.696 I because it was almost universally used by the oil and gas industries worldwide. The above definitions are no longer the most commonly used in either system of units. Current use. Many different definitions of standard reference conditions are currently being used by organizations all over the world. The table below lists a few of them, but there are more. Some of these organizations used other standards in the past. For example, IUPAC has, since 1982, defined standard reference conditions as being 0 degrees Celsius and 100 kilopascals, in contrast to its old standard of 0 degrees Celsius and 101.325 kilopascals. Natural gas companies in Europe and South America have adopted 15 degrees Celsius and 101.325 kilopascals as the standard gas volume reference conditions. Also, the International Organization for Standardization, the United States Environmental Protection Agency and National Institute of Standards and Technology each have more than one definition of standard reference conditions in the various standards and regulations. Notes: e.g. Electricity and Gas Inspection Act, SATP, Standard Ambient Temperature and Pressure, International Standard Atmosphere. In aeronautics and fluid dynamics, the International Standard Atmosphere is a specification of pressure, temperature, density, and speed of sound at each altitude. The International Standard Atmosphere is representative of atmospheric conditions at mid-latitudes. In the USA, this information is specified the U.S. Standard Atmosphere, which is identical to the International Standard Atmosphere at all altitudes up to 65,000 feet above sea level. Standard laboratory conditions. Due to the fact that many definitions of standard temperature and pressure differ in temperature significantly from standard laboratory temperature, reference is often made to standard laboratory conditions. However, what is at standard laboratory temperature and pressure is inevitably culture-bound, given that different parts of the world differ in climate, altitude, and the degree of use of heat, cooling in the workplace. For example, schools in New South Wales, Australia use 25 degrees Celsius at 100 kilopascals for standard laboratory conditions. ASTM International has published standard ASTM E41 terminology relating to conditioning and hundreds of special conditions for particular materials and test methods. Other standards organizations also have specialized standard test conditions. Molar volume of a gas. It is equally as important to indicate the applicable reference conditions of temperature and pressure when stating the molar volume of a gas as it is when expressing a gas volume, a volumetric flow rate. Stating the molar volume of a gas without indicating the reference conditions of temperature and pressure has very little meaning and can cause confusion. The molar volume of gas is around STP, and at atmospheric pressure can be calculated with an accuracy that is usually sufficient by using the ideal gas law. The molar volume of any ideal gas may be calculated at various standard reference conditions as shown below. Vm equals 8.3145 times 273.15. 101.325 equals 22.414 cubic decimeters per mole at 0 degrees Celsius and 101.325 kilopascals. Vm equals 8.3145 times 273.15. 100.000 equals 22.711 cubic decimeters per mole at 0 degrees Celsius and 100 kilopascals. Vm equals 8.3145 times 298.15. 101.325 equals 24.466 cubic decimeters per mole at 25 degrees Celsius and 101.325 kilopascals. Vm equals 8.3145 times 298.15. 100.000 equals 24.790 cubic decimeters per mole at 25 degrees Celsius and 100 kilopascals. Vm equals 10.7316 times 519.67. 14.696 equals 379.48 feet 3 lbmol at 60 degrees Fahrenheit and 14.696 I. Vm equals 10.7316 times 519.67. 14.730 equals 378.61 feet 3 lbmol at 60 degrees Fahrenheit and 14.73 psi. Technical literature can be confusing because many authors fail to explain whether they are using the ideal gas constant R or the specific gas constant Rs. The relationship between the two constants is Rs equals R per meter, where m is the molecular mass of the gas. The U.S. standard atmosphere uses 8.31432 cubic meters per as the value of R. However, the USSA 1976 does recognize that this value is not consistent with the values of the Avogadro constant and the Boltzmann constant.